This material is made available to you by or on behalf of the University of Melbourne under Section 113P of the Copyright Act 1968. It may be subject to copyright. For more information, visit the University Copyright website.
Okay, good morning, everyone. When you are ready, we'll start when you are ready. When you are ready. All right, thank you very much. So just an announcement before we start. So people whose workshops are on Fridays start this week because of grand finals. Everyone else starts from next week. So for Friday people, workshops start this week. And you will probably get an announcement soon on this. All right. So last week we presented a general introduction to this subject, and we introduced some concepts, some terminology. We also overviewed some of the topics that we will be covering in the subject. And one of the things that I mentioned a few times already is that this subject is model-based. I mean, all the tools that we will develop or present require the use of models. So modeling is a starting point in any design or analysis that you would do when dealing with a control system. Now, we will not have time to spend, on modeling of different types of systems, because this would take us too much time. So you can talk about modeling of mechanical systems. So people in mechatronics, would be interested in that, or mechanical engineering. You can talk about modeling of electronic systems. You can talk about thermodynamic systems, fluid flow dynamic systems. So each different class of systems would require different types of models. Quantum systems would require tools from quantum mechanics to actually develop those models. So what we do need to do, and we will do that in this lecture, we will connect material from this subject with some examples of models. So typically I won't ask you to derive the model from scratch, but I will give you the model, and then you would need to interpret it and use it for the purposes of this subject. Right? So you need to know how to use models in designing and analyzing control systems. Now, we do need to make this link. And this lecture is very important because it provides a link between physical models, right? So everything we do is to do with something with physical systems, and mathematics that we will be developing and concentrating on in the subject. So often students say this is a very mathematical subject. Well, it does have relevance to physical systems, and this lecture provides this link. So today we will talk about modeling from first principles. I already presented in lecture 1 this block diagram, and I talked about different types of models. By the way, I remind you that the boxes contain systems or subsystems, and arrows denote signals. I told you also that we will deal with different types of models in this subject, and we will develop different classes of tools for each different class of models. So one class of model is when we model signals as continuous time functions, right? Functions that change with time. So maybe a signal may be a temperature in the room that changes with time, right? Over 24 hours, there are oscillations of room temperature. There can be pressures, speeds, positions, anything really, any physical variable. And then the system itself is described by either an algebraic equation or differential equations. So that's one class of models, and actually that class of models would be the focus of today's lecture. We will typically start from a set of differential equations, and we might then go and introduce transfer function to analyze those, or use some frequency domain methods like Bode diagrams, Nyquist plots, and things like that. So we will concentrate on these models later in the subject, but in today's lecture we provide the link with physics, and we will talk about these differential equations. All right, so here is the outline. I'll first motivate things. I really want to emphasize the importance of modeling. Modeling is an art. So each model is useful for something, right? Maybe they are useful for design, for analysis, for simulations, for prediction. They are important. I want you to appreciate, from this lecture, I want you to appreciate just how versatile and how useful models are. So we will talk about the general approach, to modeling from first principles, and we will present a number of examples. I probably won't go through all examples. They are there in the slides to sort of help you, to help guide you. Please study those examples on your own if we don't manage to cover everything. You can open any book. For instance, Ogata's book or Franklin and Powell book would have several chapters dedicated to modeling of different classes of systems. Mechanical, thermal, hydraulic, pneumatic, name it. I mean, they have everything there. So you will get samples of a range of different models in these books. One amazing thing about this subject is that this subject can help you design and analyze any kind of model. Doesn't matter where it comes from, as long as you do a good job in representing your system with your model. You can apply the same tools for mechanical systems, for thermodynamic systems, for fluid flow systems, etc. So generality of this subject is really means its widespread use, right? So it can be used in any area of engineering. So we will maybe, if we have time, talk about model classification, simply so that you realize that the tools developed in this subject are just a small subset of all possible tools. We will consider a very, very special class of models throughout the whole subject. But it's good to put things in perspective. And if we have time, we will talk about classification. And then I will just wrap up. All right, so what is a model? Well, it's a mathematical description of your system. Right? It can be described by some, algebraic or differential equations. And how we think in this subject, we think about models as relating some input signals to some output signals. So just to remind you, in room temperature control example, input signal may be the desired temperature of the room. So you set the desired, you tell the system what temperature you want. It may be disturbances outside. That may be an input to the system. But the output of the system is the true temperature in the room. That's the signal you are interested in. So model would then relate all these inputs to these outputs, right? And depending on the system you consider, you may have different inputs, different outputs. But a differential or algebraic equation that relates these inputs to the outputs is the model of the system in our language. By the way, if you have, let's say, this as your system. It's like a seesaw. I may say, well, I would apply some force here and move this side. Well, this may be the input, and whatever happens here may be the output. How you define inputs and outputs depends on the particular situation, right? And we talked about these general definitions. Output is something you are interested in, and input is anything that affects that variable, right? How you can think of models, and this is a very abstract view of models, is you can think of a model, basically it tells you how set of inputs maps to set of outputs. For instance, in this seesaw example, if I apply sinusoidal input, which is this movement of this side, then the output changes sinusoidally, right? So sinusoidal input, sinusoidal output. If I apply fixed input, I get fixed output. If I get slowly varying, exponentially sort of decreasing input, I get similar output. Now, what's interesting is that static systems would have this static relationship between inputs and outputs. So for any given input, there is a single output, right? So whereas dynamical systems, for the same input, they may produce different outputs. So what is a dynamical system? Well, it's myself, right? If I want to get up and exercise, right? If I'm fit, I will do well, I will do a lot. In the gym, I can lift more weight, I can do more cardio, and I would feel good afterwards. But if I'm not fit, if my initial condition is different, I will feel bad. If I'm sick, I will feel horrible. So the output, when I apply the same input, I try to do the same thing, but that would change depending on my initial state. That's dynamical system. So dynamical systems are systems where some internal memory would affect what the output you get for the same inputs. So in other words, if you perform an experiment to dynamical system, you might get different outputs for the same input. And that different output would depend on the initial state in your experiment. But abstractly, you can think about your system. It's like a mapping. Abstractly speaking, it's a mapping, mathematical description that maps a set of inputs to a set of outputs. That mapping may not be unique. It is unique for static models, but for dynamic, it's not. The same input might map to multiple outputs. Okay? So we can roughly classify models into static and dynamic using the sort of this test that I was telling you about. So static systems have the same output for a given input. Dynamic systems actually may produce different outputs for the same inputs. And they depend on the so-called state of the system, right? So room temperature control, that's a dynamical system. Why? Why is it a dynamical system? Why would this room temperature control example be a dynamical system? So it depends on the initial room temperature, what the output would be. So if I turn on a heater and I turn it on at 35 degrees initial temperature in the room, it would heat up very quickly to some higher temperature. If I have initial temperature which is minus 25, it will take for the same heater input, a long time to warm it up to some, temperature I want. So obviously it's a dynamical system, right? It depends, its behavior depends on the internal variable in the system. So what we want to do is we want to talk about different types of models and present different examples. And also emphasize importance of models. One purpose of today's lecture is to emphasize importance of models. So I like this quote, and I don't know who really, first said this, but it is attributed to George Cox. So it says, all models are wrong. All models are wrong, but some are useful. And it's very, very true. So you cannot expect to have exact replica of your system in a model. You cannot expect that. There are too many variables and things that you can't account for when modeling the system. But many of them are useful for different reasons. And we will list some of these reasons in today's lecture. And you will, in your labs, see how models are useful, because what you will do, you will have a Lego robot, you will first identify it, fit sort of a model to experiment, you will perform an experiment, come up with the constants in your model. Some things were obtained from first principles, right? And then you would use that model to design controllers, and you will see that they work. That's the beauty of it, right? So you will see that these models that you would develop in labs would be useful. So we will hopefully convince you throughout the subject that this is the case, that models are very useful. So why are they useful? They are used for various purposes. One is, just understanding input-output relationships, maybe for prediction purposes. If you have, let's say, so for instance, in meteorology, people try to predict climate change. How would temperature change in the next 20 years? They're trying to predict based on some assumptions on carbon dioxide emissions, et cetera, right? So they are building very massive models to try to predict what would happen 50 years from now. And then they talk to senators or ministers or whatever, the government, and then government imposes some regulations. So models in this context might be actually influencing how expensive your car is. If emissions are suppressed, made tighter, the control systems in the car would be more expensive. Or you might have to resort to electric cars, right? So you don't realize actually how much you may be affected by models. Controller and estimator design, this is what we do in this subject, advanced control, advanced motion control. That's what control subjects are all about. It's all about design. Also evaluation. So you might use a simpler model to design your controller and then use a much more complicated, higher fidelity, like a better model, to evaluate your controller. It's still safe because you're running simulations, but you are safer in doing that step than implementing your controller directly on your system, because things may blow up. And especially if you have safety critical systems like aircraft, you will do a lot of simulations before you do test flights. And still, disasters happen. So there was a big disaster where a test flight basically crashed. The pilot survived in Sweden. I think it was Saab, one of the Saab planes. What happened was they designed controller based on a simple model. They evaluated it on a better model, but better model still didn't account for some crucial issue in actuators. What happened was you could not change actuators quickly. So there were these sort of control surfaces on the aircraft, and you could not quickly change them. There was a speed limit that they did not take into account. And when they pushed the plane to an operating regime that couldn't cope, basically, with this constraint, the plane crashed. You can imagine how many millions of dollars, pilot's life was at stake. And this is because, some crucial thing wasn't taken into account in modeling, right? Now, model complexity depends on their intended purpose. In this subject, the advice is to work with the simplest possible models that capture all the crucial dynamics, or all the crucial issues. So that's why I'm saying modeling is an art. Picking the right complexity of the model is already a sort of an engineering challenge. All right. So we will hopefully teach you how to do that, and you learn by doing. The best way to learn is by doing. All right. So why do we do this also? Other motivation? Well, everything in this subject will be based on models. So without models, you can't do any of the designs or analysis that we will present. It's a typically first step. And, this lecture is essential, as I said, because it links physics to mathematics, right? All right. How can we do modeling? Well, we can do from first principles. This is a name we give to sort of approaches that use physics, thermodynamics, any sort of mechanics, physical laws to develop relationships between inputs and outputs. So Newton's laws of mechanics is one example of such first principles. Kirchhoff's laws, Ohm's law, they are all examples of first principles or laws of nature. So we can also, that's the first approach, we can also get models from simplification. One particular type of simplification is called linearization, and we will learn about linearization in this subject and also advanced control. A linearization is basically an approach where you simplify a nonlinear model by a linear model. So linear is simpler than nonlinear, around an operating regime called an equilibrium. So we talked about equilibria, but linearization approximates nonlinearity around a specific operating regime. So we will talk about linearization, I think, tomorrow. Model reduction, you might have a very high dimensional dynamics, and some dynamics may be fast, some may be slow. But you may not be interested in fast dynamics that die out quickly, perhaps. You might be interested only in slow dynamics. Then you can talk about reducing the order of the model, and these methods go by the name of model reduction. Discretization, if you do advanced control, we would learn how to discretize the model for the purpose of using in digitally controlled systems. Any sort of controller or microprocessor that is used to control your system is digital in nature, whereas processes that we typically want to control are continuous in nature. So by discretization, you can simplify modeling for that class of systems, etc., etc. So from data, you will learn how to perform experiments in your labs and then find parameters in your model. So you use an experiment to basically build a model, right? So there are all sorts of different approaches. And, we will concentrate in this lecture only on first principles. So, but there are all these other approaches just to give you sort of a better understanding and context. So we just go through all these. So we want to now concentrate more and more on models from first principles. This is basically from laws of physics, mechanics, fluid dynamics, etc. And in order to do this, I need to explain an important notion, which is basically the importance of assumptions. So what are assumptions? Assumptions basically specify operating conditions for your model. For instance, if you want to model me, you may make assumptions. He's not sick, right? He's whatever, fit, he goes to gym, he had food, he slept well. That would give you one model, right? These assumptions would give you one model of me, right? If you say, well, he's actually very sick, right? Well, that would give you a totally different model. Also my age, my fitness, my whatever, right? So it's just these assumptions say, for instance, for a car, what sort of operating assumptions, conditions you are assuming, and your model would only be valid if those assumptions are valid. If you change the assumptions, the model would necessarily need to change, most of the time, right? So we do not state all assumptions in our examples, but what I will try to do, I will present several simple examples where I illustrate the use of assumptions, and then later on I will go quickly over some models, but all of those assumptions still hold, right? If we do mechanical systems, all the assumptions in Newtonian mechanics would need to hold. All right. So the question is, how do we use these assumptions? Well, this is a very good quote. Well, the model should be as simple as possible, but no simpler than necessary, right? And this goes back to what I said earlier, that you want to really capture the main sort of processes, main dynamics in your model, but you don't want to work with something that's too complex that you can't analyze, that is useless for design. The more complex the model, the less design and analysis techniques we have at our disposal. That's why we would work in this subject with the simplest of all models, which are linear, deterministic, continuous time. They are the simplest of all models. All right. Let's first look at static models. So I remind you that static model would basically be model where we have that inputs and outputs are related by an algebraic equation. And you know, this seesaw example, this is the input, that's the output. If I assume that this is rigid, it can't bend, well, whenever I set the certain value of input, that would produce same value of output, always the same value of output. That's an example of algebraic system. For instance, you might have, you know, that this describes your model. This can be a model where this may be, I don't know, force, you know, or displacement, you know, of something, and this can be displacement of something else, like in a seesaw example, if you assume that this is like a nonlinear model. What this means, well, if I now apply certain input which is a function of time, so maybe this input here changes sinusoidally, well, you can compute from the model what the output would be. So model can be used to predict what the output would be if I give you a certain input. I can give you any input, and the model would be able to predict what the output would be. It's a static relationship. Do you remember any static models from physics, mechanics, thermodynamics? Do you remember any static model? Can you tell me what would be a static model that you have already studied? Ohm's law, that's a very good one. Yes, Ohm's law, and I will actually talk about that in a moment. It basically, in electrical circuits, it relates, you know, voltage and current through a static relationship, right? So we will talk about that. In mechanics, do you remember any static models? Force in a spring. So if you have a spring with certain assumptions, the deflection of the spring would be proportional to the force under certain assumptions. So let's go through several such examples, and in these examples I would be a bit more careful about specifying assumptions under which these equations or models are valid, so that you just understand the importance of these assumptions. Often in electronics or, you know, in mechanics, you don't repeat these assumptions all the time, but they were repeated the first time you saw those equations. The first time you saw those equations, those assumptions were stated. Here's Ohm's law. So if you have a resistor, you apply certain voltage to this resistor on both sides, then that would cause certain current to flow through the resistor. So the current is I, the voltage is V, and then resistance of the resistor is R. Now, Ohm's law states, and you may have seen this, that voltage is equal to R times I. R is constant. You give me a resistor may be 100 ohm or 1,000 ohm or whatever. It can be, it's a fixed value, right? And then you have this static relationship between voltage and current. The higher the voltage, the higher the current. The constant of proportionality is R. It's very similar to this seesaw example, right? I apply certain input, I get certain output all the time over there on the other side. Now, you may not have been very careful about what are the assumptions under which Ohm's law holds. Now, first is, well, resistor is made of so-called ohmic materials. Not all materials would behave like this. And I mean, semiconductors, for instance, they won't behave like this. So the assumption is that you made the resistor from an appropriate material, right? The second assumption is, well, temperature is constant. You would find that resistance changes drastically as you lower or increase temperature. One assumption is that, well, current is sufficiently small. You do not sort of trigger some nonlinear effects. If you increase, you know, the voltage, right, you would burn resistor. Light bulb is like a resistor, light bulb, and it burns if you apply too high voltage, right? Aging is ignored. Well, nothing stays the same forever. Here, aging is, you know, totally ignored. So look, when you write this equation, you know, you don't think about it. You just write it down. But it is only valid if a range of different things hold. Now, without understanding these background assumptions, you would not understand what this equation represents. It only represents behavior of a resistor under specific operating conditions. So when you are modeling for control, my strong advice is that you list carefully every assumption that you use to develop the model. Why is that important? If you design your controller based on your model, you implement it on the true system, and it doesn't work, one of the first things in sort of finding a problem is to check whether your assumptions are valid or not, whether your operating conditions were really captured by the assumptions that you use to derive the model. So always list all your assumptions clearly. Assumption 1, blah. Assumption 2, blah, etc. Right? Very, very important. Here is another one. So we already mentioned this. So another static model. We have that force in the spring would be proportional to the deflection of the spring from its sort of zero sort of length or displacement. So force is proportional to ky. K is the constant of proportionality. Now this only holds if you stay within certain operating regime. If y becomes too large, you will just break the spring, right? So you just keep extending it and extending it, you will break it, right? This only is valid for so small deflections. So then you can use this sort of proportional, static modeling. All right, so are there any questions? Are there any questions so far? No? All right, let's go to dynamic models now. I want to present a number of examples. We will see how far we go. I will try to go slowly so we understand things. But I encourage you to go through all these examples and go through Ogata and Franklin and Powell books. They have a lot of examples. The more examples you see, the more comfortable you will feel when you encounter a new example in an exam, right? So you need to be comfortable with using these models, right? Manipulating them. All right, let's look at dynamic models. So what are they? Well, the difference with static models is that now the same input might produce different outputs. And how do we model this? Well, with differential equations. So depending on the initial condition of the differential equation and input, you will get different outputs. So if you have, for instance, this situation, this is called an integrator. Note that the y dot is equal, u is an integrator. Why? Because I apply input, and what is the y? It's an integral of u. Right, so this is an equation of an integrator. Many physical systems would have this sort of model, right? Think about capacitor or inductor. Depending on how how you define your inputs and outputs, you would get this sort of equation. So if you integrate this equation with certain initial condition, well, know that there is this y0 which you need to know, right, in order to integrate the equation. So depending on the initial condition and depending on the input, you will get different outputs. So that's an example of a dynamical model, right? We need to come up with a differential equation. By the way, for people who forgot about this, y dot represents derivative with respect to time, so dy dt. So this basically says that dy dt is equal to u, right? We will now go through a number of different examples. We will obtain different dynamical models. I will try to present a mechanical system example, maybe fluid flow example, etc., etc. And we will try to identify different features in each of these, right? So that you just start building some sort of feeling for, what do we call dynamical model, right? Here's one example. What I did here is I just complicated my string example just a little bit by attaching some mass to the spring. And also, I have now some force U, right? So there's some force U that is applied to the mass. I have mass in kilograms, and I have this spring that is connected. I would neglect, so note that this model is derived under a set of assumptions. First, Hooke's law for the spring holds, so displacements are small. I didn't stretch string to break it, right? Newton's second law holds, so mass doesn't move at the speed of light, right? So it's Newtonian mechanics applies. By the way, the speeds at which we move you change assumptions. So relativity theory basically was developed because assumptions of Newtonian mechanics did not apply anymore. And you had to redevelop new theory. That's an example of how assumptions are important. So here we assume Newton's second law is applicable. We assume no friction, no damping. So I assume that there is no friction force. Typically, you will have friction force. All mechanical systems have some friction. So know that what I'm saying here is that this no friction is an idealization. The model that I would get would not correspond to any real system. But if the friction is very, very small, and you can reduce it by just lubricating the surface where mass is sort of touching the ground or something, like it's sliding maybe on some surface. So you can get this friction constant to be very small. But here we assume that there's no friction and no damping. So if you do that, then Newton's second law basically says that mass times acceleration in y direction, which is y double dot, is equal to the sum of all forces acting on the mass. Because we assume that only spring and outside force U act on the system, that's the model. So note what I have here is my input is a force, and the differential equation that describes the system under these assumptions is given there, right? So that differential equation, you give me any input and give me any initial condition, I can calculate the output using this model, right? How would this model change if I had some friction? There will be another force. So if we assume, let's say, damping friction. So force is damping, so friction force is proportional to velocity, y dot. How would that change? We will get another term here, maybe k1 times y dot, right? So there will be my double dot plus this friction term, because force U is moving things, and everything else is opposing this movement, right? So by the way, assumptions affect the model. And you have to be careful about what operating regime you are specifying and which equations you are writing, so that they relate to assumptions. I change the assumptions, the model needs to change. Questions? All clear? All right, we're going well. Here's another one, electrical circuit. Now I have, a circuit that contains inductance and capacitance, right? Capacitor, inductor, right? And I have a resistor. So what I'm saying here, I identified that I wanted to use this voltage as U. Voltage U is given there between those 2 points. But then I'm saying I'm interested in the voltage across the resistor. That's my output. That's, depending on the application of this circuit, that may make perfect sense. So what would be assumptions? Well, that Ohm's law can be used for the resistor. Now we use equations of ideal inductor and ideal capacitor. Note that you may have seen these equations that relate voltages and currents, right, across the inductor and capacitor. These are idealizations, and again, they are valid only under certain assumptions. I'm not specifying, listing all those assumptions. Again, if I apply too large voltage, I can burn capacitor, I can burn anything. If I, hit it with a high enough voltage. So, and also Kirchhoff's current and voltage laws hold, right? Again, these are valid only under certain conditions. Well, if you satisfy all those assumptions, then you can write a differential equation that looks like this. Now, for people who have done electrical circuits, they would understand how to derive these equations. I won't do that in this lecture. I encourage you to go to Ogata to sort of learn a bit more about these laws. This is not the focus of this subject. The focus of this subject is take on board whatever models you have and then work from that point. So I won't go into details of how to write something like this down. But the interesting thing that I want to point out is when I think about just inputs and outputs, know that this differential equation is very similar to the previous one, right? So as soon as I identified inputs and outputs, I deal with the same mathematical object. So we will take this mathematical object and do all sorts of magic with them, right? We won't care where it comes from, whether it's an electrical circuit or mechanical system. That's the power of this subject. It can apply to any area of engineering or natural sciences. People use it in social networks, in neural science, any area, right? So it's a very powerful set of tools. Here's another one. We have here fluid flow system. So we assume law of conservation of mass, constant cross-section in the tank. So what happens here? You have a valve there. There is water flowing through and flowing into the tank. And then there is some outflow, but the outflow can be shown by, Pascal's law or whatever, that you basically have that it's proportional to the square root of the depth of water in the tank. The more water you have in the tank, the higher the pressure here. And if you are flowing out, if this is atmospheric pressure, here this pressure will be pushing water faster. If you have more water in the tank, it would flow faster. And the constant of proportionality is square root of y, where y is the depth of water in the tank. So if you use all of these things, you can again say, look, the first thing is really dv dt. I already presented in the first lecture when we talked about equilibria and water clock. I showed an equation of how tank is filled up with water. So whatever volumetric flow we get inside the tank, right, you subtract volumetric flow out, and that produces the change of volume in the tank. So this first term, A times y dot, is really the derivative of volume of water in the tank. And then what is this equal? Well, it's really inflow and outflow. But what is interesting about this case is outflow is proportional to the square root of y, but inflow here has this interesting t minus tau, right? So what is this trying to capture? It's trying to capture delay. If the valve is very far from the input, so for instance, this is, maybe a kilometer away. If you open the valve, it will take water some time to get to the tank. So, and that's captured by this delay, this tau. So that tau is the delay. And by the way, there are many, many control systems where delay is present. I act now, but I see action only later. That's captured by this delay. So this model is described a differential equation, but it has two different features from the previous two models we considered. First, it has nonlinearity. Square root of y is a nonlinearity. That spells trouble. That spells difficulty. Nonlinear models are harder to deal with. We will just use them to linearize these models, approximate them with linear, and then we will get something like in previous two examples. And then we will use that as a starting point in this subject. Delay is also very difficult to deal with. It may cause instabilities, very, very hard thing. If there is a delay in communication between people in a gossip situation, it's disaster. Right? You probably experienced, you talk to a friend, that friend talks to someone else, they tell them what you told them with some sort of noise and delay. Then you say, oh, how could they say that? And then it takes you time to talk to the other person. But then, that this delay can cause big problems. Another example is, this delay here in water flow system. If you've ever rented a very poorly built house, if you're sharing accommodation, and maybe there is a mixer where you mix hot and cold water, and then it takes a while for the water, if the water is really far away, the outlet, there's a shower, by the time you change the mixer, it takes time before you start feeling the effect. And you know that those showers are unpleasant because you go, ooh, cold, hot, delay is a nasty beast. So this is one example of a different kind of model, which is derived under different sort of assumptions. So we are getting to the end of the lecture. I want to sort of show you just two more things quickly. So I love this example because this is my teaching tool. So, and this is exactly the pendulum that is modeled here, right? The assumptions here are that the string here is massless. There's no mass in the string. All mass is concentrated in the bob, in this mass here. Arm is rigid and massless. There's no friction, etc., etc., etc. What you do again is you will need to apply Newton's laws of motions. Here it's done by writing Newton's law of motion in horizontal direction and vertical direction. So you split all forces into horizontal and vertical component. If you do that carefully, first you can rewrite the mass by replacing, you replace all sort of like action of the bob by forces in horizontal and vertical directions. So if you use then, Newton's second law of motion in horizontal and vertical direction, you will get something like this under certain assumptions. Now, after you eliminated some of the things, so by the way, this is no more difficult than just a mass and spring. It's no more difficult. You just have more forces acting on the system. So if you do some sort of manipulations, you can eliminate force in the arm to obtain this model. Now, note what is interesting here. You have mass, you have the length of the string, right? And then you have this theta, which is the angle that this swing or pendulum makes with the vertical axis, right? So what this tells you, well, ml theta double dot, that's the theta double dot is angular acceleration. Angular acceleration. And then you have here two things. Look, this depends on cosine theta, this depends on sine theta. G is just the gravity constant. So you have mass, length of the pendulum, and gravity constant. This model is nonlinear. Why? Because the output, in this case, theta, enters nonlinearly. Cosine and sine are nonlinear functions. Again, you can learn to linearize this model. So suppose, by the way, let's look at the. So theta is basically the angle, right, between the vertical and the true position of the string. So basically, theta equal to 0 corresponds to this position, yeah, and theta 180 degrees corresponds to this position. Let's look at the model. What would be, if I have that, theta is small, how can I, simplify this model? Well, for theta close to 0, cosine is close to 1, and sine is close to theta. If you think about sinusoidal function, if you take tangent at 0, it's basically just a straight line theta. So I can linearize this model around this point for small oscillations. If theta is small, I can replace cosine by 1 and sine by theta, sine of theta by theta. That's a simple example of linearization around this operating position. If I have this position, what happens then? Have 180 degrees. So sine minus theta. Now sine is coming down, so the slope is in this direction. And how about cosine? Yeah, so you see the model, the linearized model, change depending on which equilibrium we considered around. So this nonlinear model can have infinitely many linearizations depending on which equilibria we are approximating around. And that's the topic of linearization, right? We will talk about linearization in detail in the next lecture. All right, there is another example of DC motor. You just work through this. I just want to do one more thing before we wrap up. So this is a classification of all possible models. There are so many different classes of models. So in telecommunications, people like to use stochastic models, because all phenomena are described using probabilities. In mechanical engineering, often you are happy with deterministic models. You can talk about linear and nonlinear model. We saw several examples of nonlinear model in this class, and we also saw how they can be approximated with different linearized models around different equilibria. They can be statico-dynamic. We also saw that. They can be finite dimensional or infinite dimensional. Finite dimensional, think of it as you need finite amount of data as its initial conditions. So for instance, the RLC circuit is a finite dimensional model. So is the mass with a spring, and so is the example of the pendulum. The infinite dimensional model, the only infinite dimensional model that we consider in this class is the time delay model. Why is this? Because in order to integrate equations, you would need to know input for all time between 0 and minus tau. Because you may have different profiles that would affect the solutions of the system. So you need basically a piece of function which is an infinite dimensional object. Anything described by partial differential equations is an infinite dimensional object. Navier-Stokes equations, Maxwell-Boltzmann equations, they're all infinite dimensional, right? So you can also have time-varying models and time-invariant models. Anything ages. Anything changes with time. We often do not capture that. Most of the time we do not capture that by our models, because we consider that during the time that we consider the system, the system doesn't change much. And you can approximate this by time-invariant model. Now, when you bear this in mind, look at this. Our focus in this subject is this class of models. We concentrate on deterministic, dynamic, finite dimensional, continuous time, linear, time-invariant models. It's such a small subclass of all possible class of models. It's the simplest class to consider. However, you will see, and you will get convinced through your labs and different sort of exercises you do throughout the semester, this is a very useful class of models, because many systems can be well approximated by this class of models around certain equilibria. So although it's a very simple class of models, very, very special class, it's extremely useful. And we will concentrate only on this. So if I drew, sets of models, this may be, stochastic, nonlinear, infinite dimensional, blah, 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 time varying. But we use, just a small subset of this class. And still it will prove to be extremely useful for everything that we do. All right. So what we talked about today is we talked about models. What's a model? It's a mathematical description of the system. We saw that models can be obtained from first principles, and assumptions specify the operating regime for which the model is valid, right? Control-oriented models need to be as simple as possible, but no simpler than this, right? So you can approximate a circle by a square, but that's not a good approximation, right? So in many examples. So we also shown several examples of models, and if you open books by Ogata or Franklin Powell, you would have a whole library catalog of different models. I encourage you to study these, because it will make it much easier for you to just handle these things in the context of this subject. Questions? All right, thank you so much, and I'll see you tomorrow.
有点嗓子有点烧，我待着。今天下午知道吗？